Hey guys, so this is going to be a neural network tutorial video. I asked in my last video if you guys wanted to see it, and a few people said yes. So this is going to mainly focus around how to create neural networks that evolve over time through mutations. This will not be supervised learning where you backpropagate the error. This will be unsupervised learning through mutations over time. I might do a video on supervised learning in the future. Since my channel mainly focuses on neural networks that mutate over time to acquire certain skills, that's what I will be focusing on for this video. But the idea of a feed-forward neural network is still the core concept which you guys would be learning from this video. I'm gonna probably go out on a limb, and I hope this isn't too cocky of me, but I do think this is going to be one of the easiest to understand neural network tutorials on YouTube, period. I think I'll have a very easy way of teaching this to you guys, where we start from the bare bones and we build a neural network from there. First things first, I'm going to have to ask you guys to go to Unity. I'll have a link to this in the description, and just download the free version of this, personal free, okay? And we're going to be programming this in C#, but I'm asking you guys to download Unity because I want to make a pretty cool little project with this. So eventually, after we're done programming our neural network, we're going to use that to do something pretty cool in Unity. Okay, it's free, so I mean, I think it's just worth downloading this. And it comes, I think if you install this, it comes with Visual Studios, so that's perfect. So now I'm going to get into the concept of a feed-forward neural network and how we can create data structures for it in a programming language. One thing that I am expecting from you guys to already know is have a background in at least one programming language. It could be anything, just a basic idea of at least one programming language. Have basic ideas of things like primitives and reference variable, concept of object-oriented programming, and some ideas of really easy data structures, you know, things like arrays and lists. This is pretty much what you need to know before we continue on into this video. But if you don't know those, I'll have some link in the description that you guys can go watch first. There's some amazing videos on YouTube, and then come back to this video. Otherwise you're going to be just a little bit lost, because I'm not going to spend my time explaining those basic concepts, but I will be explaining them in terms of neural network and how we can use them. So before we go to the programming part, we're just going to quickly go over what the data structures will look like when we program this. First thing that you will notice is that each layer might have a different number of neurons, right? So the first layer has 4, whereas the third layer has 3, and the last layer has 2. So we know that each layer can be represented by an array. So this is the first layer up here. And what do we call the combination of all these layers together? So these are all neurons, and we need to combine the layers for every single one of these together into a one giant array, almost like a two-dimensional matrix. However, every single row within this matrix can have a variable length. In C#, this idea of having n by m matrix where m is a variable length is actually called a jagged array. This symbol in C# means a jagged array. There are a n number of layers that you can specify. In this case, there are 4 layers. So this number of layers would have been a 4, but for each row in that two-dimensional array, this part here can vary in length. Some of you guys, if you have done Java before, you might get confused. This in Java is actually a square matrix, whereas in C# it's actually a jagged array. Okay, so don't get confused if you've done Java before. So now we know what our neuron matrix is going to be stored as, right? Just a jagged array two-dimensional matrix. But what about our weight list? You know, all these connections that are represented, these black lines here, what about those? How are we going to store those? That's also very simple. It's just going to be a 3-dimensional jagged array. This here is a 3-dimensional jagged array. You're probably wondering, well, why are there 3 layers in here instead of the previous 4 that are in the neuron matrix? Well, that's simple. That's because this is a weight list, and the input layer does not have any incoming weights. So what does this 1, 2, 3, and 4 represent? Well, this 1 represents this line, the 2 represents this line, the 3 represents this line, the 4 represents this line, okay? So this first array here is actually all the connections of the first neuron in the first hidden layer, followed by the second neuron in the first hidden layer, followed by the third neuron in the first hidden layer, okay? You can see that the last neuron, the bias neuron, which is over here, has no incoming connections, so it's just going to be a closed matrix with a size of 0. In our program, we might not even add it as part of this matrix, but just as an example, understand that because the bias neuron has no incoming connections, its size is 0. Now, same thing with this 1 right here represents this neuron and this connection, and the 2 represents this, the 3, and finally the 4. Okay, you can see that this here, the size is 2. That's because there are only 2 hidden neurons that actually have weighted connections, whereas the bias neuron has no connections, so it's just size 0. And similarly for the output has no bias neuron, there is no closed empty matrix. And this will be our little code for the weight matrix, and that's it. Just with these 2 data structures, we will build our neural network. If you can understand just this basic concept of how a neural network is structured in a matrix, the rest of the video will make perfect sense to you. So just double click on Unity, click New. I'm gonna name this project Neural Network Tutorial. You can name it whatever you want. I'm just gonna select 2D, but you can select 3D if you want. It's gonna be a 2D project, so just select 2D and just click Create Project. So first thing I'm gonna ask you guys to do is right click, go into your Assets folder, right click, click Create, click Folder, and create a folder called Scene. And then right click again, create another folder, this time called Scripts. Okay. Now click File, save scene really. Go to Scene. I'm just gonna name it Neural. When this is done, now go into your Scripts folder, right click, click Create, click C# script. I'm gonna call this Neural Network. Double click on this C# file to open it. It should open with Visual Studios that you installed alongside Unity. It'll take a little while to open when it opens for the first time. So first thing we're going to do is remove these 2 methods here since we don't need them. And we're just going to remove this mono behavior here since that's a parent class for game objects, and well, we don't need that with a neural network. Also remove these 3 imports here. We'll import things as we need them, and at the moment we don't need these. Let's create our constructor. So this will be our initial constructor where we will feed in the layers and it will create our standard neural network for us. So we're obviously going to need some layer array to store that information. And we also need the 2 data structures that we talked about previously. So for the moment, these are the only variables that we need. So we need to get this layer information into this neural network constructor because the neural network needs a layer information to be able to create the neurons and the weights. So we've initialized our layer, which has been passed into to the constructor, but now we need to create our neuron matrix and our weights matrix with this layer information that we have. So we're going to need 2 methods. So now we have our initialized neuron method and we have our initialized weights method, and in this we will generate our neuron array, and in this we will generate our weights array. So let's first create the neuron array. So first thing we're going to do to create a neuron array is actually create it using list. And then once we're done creating a list, we will convert that list into a jagged array. So this is a method of converting from list to a jagged array. So first of all, we have a list of float arrays. that's quite literally what our neuron list is. If you think about it, there's a number of layers, and each layer has its own float array, i.e. the number of neurons in that array. So this is also another way of kind of thinking about what a two-dimensional matrix looks like. If you're getting this error, just go to show potential fixes and import using system collections generic. So list is a generic, and essentially what we're doing here is we're iterating through the number of layers that this neural network will have, and we're creating a new float array based on the number of neurons in that layer, and we're adding it to the neuron list. This list actually has a pretty cool built-in method called toArray, which just converts list to a jagged array, and we push that into our neuron matrix. This right here generates your neuron matrix. So now let's create our weights array. So I'm just going to copy this neuron list up here. I'm going to change the name to weights list. So this weight list is going to be a list of two-dimensional float jagged arrays, and we're going to be creating these float jagged arrays in a for loop as we iterate through the number of neurons and the number of weight connections that each neuron has. One thing that we're going to be doing is skipping the biased neurons, but we'll rather just add a constant bias in our feed forward. For big neural networks, the role of a biased neuron generally diminishes, but however, it's pretty important for small neural networks. But in this case, just for the sake of simplicity, we're just going to skip the role of a bias for now. So now what we need to do is iterate over every single neuron that does have a weight connection. And it starts with the first hidden layer, so technically the second layer, which in this case in our layer matrix is the index 1. So each layer will need its own weight matrix, right, for its neurons. But this list of float arrays is a layer weight list that will essentially take lists of float arrays, and these float arrays representing the actual weights for every single neuron. So you know that each neuron connects to many neurons in the previous layer, so that's an array of float, and there are many neurons in any layer, which is a list. So a list of float arrays. Now let's get a variable called neurons in previous layer, which is just layers at I-1. We're basically just saying, well, how many neurons are there in the previous layer? Now the next thing that we need to do is iterate over all the neurons in this current layer. So the first thing that we're doing is running through all the neurons in this current layer. We're creating a neuron weight, which is all the connections of this current neuron that we're currently targeting. What are all the number of connections that are connected to this neuron, and we're iterating through all those connections, and we basically want to give it a random weight. So the first thing we're going to do is come up here and type using system. This will allow us to import the random library. Okay, and now let's create a random object, and we're going to pass in a seed that, and this is something that I pass usually whenever I'm using this library, which is system dot datetime dot tick, sorry, not dot today dot milliseconds. Okay, it's just a random seed that we pass into our random object. Neuron weights at k is equal to random dot next double. So this is going to create a double between 0 and 1, but we want to limit it to between negative 0.5 and 0.5, so I'm just going to subtract off 0.5f from this. But this is still giving an error because it's expecting it to be a float, so just cast it to a float. That's it. So now we have our neuron weights populated, and essentially when this neuron weights is done, we just add it to our layers weight list. Once we're done adding it to our layers weight list, we want to convert this layers weight list to a two-dimensional jagged array float and add it to our weights list. Weight list dot add layers weight list dot toArray. So now our weight list has a jagged two-dimensional float array, and once we're done iterating through every single neuron that has a weight connection, we want to convert this weight list to a three-dimensional jagged float array, which is just going to be our weights is equal to weightlist.toArray. And we're done. So now let's write our feedforward method for our neural network. Currently it's giving an error because I'm not returning any, so I'm just going to return null. Now, one thing that we want to do is iterate through these inputs and put it into our input layer in the neuron matrix. And we're basically going to put the contents of this input into the first layer in our neuron matrix. Now we basically just dump the contents of this input parameter into our input layer of our neuron matrix. Similarly to what we did up here, we need to iterate over every single neuron that actually has a weight connection, which starts from the second layer, which is index 1. Let's copy this down here. Now we're iterating over every single layer starting from the second layer. Next thing that we need to do is iterate over every single neuron in each of these layers. So now we're iterating over all the layers except for the input layer, and we're iterating over every single neurons in those layers. Now what we need to do is iterate over all the neurons in the previous layer. This current neuron that we're here at the jth index of neuron at the current layer is connected to some amount of neurons in the previous layer. So we need to iterate over all the neurons in the previous layer for this current neuron that we're targeting. We need to make a value that is ultimately going to be computed from the summation of all the neuron values in the previous layer with their weights. That will be value. And I'm just gonna make it give it a constant bias of 0.25f. Let's add value plus equal is equal to, we need to get the weight at I-1 because the weight matrix is one layer shorter because we're starting from the second layer, so we need to get the weight at I-1. So weights at I-1 at j, which is the current neuron, at k. And we need to multiply this with the value in the previous neuron, which would be neurons at I-1 at k. Now, once we're done calculating the value for this neuron, we need to place this value back after applying an activation to it. And I'm just going to go with hyperbolic tangent activation, which will just convert this value between -1 and 1. That will be neurons at I at j. Neurons at I at j is equal to math dot, there should be a tanh function here, of the value. And just cast it to a float so it stops giving the error. And we're done. This has now calculated the new value of this current neuron. The next thing that we need to do is actually return the output layer. So we're just going to return neurons at neurons.length -1. That's it. So we're returning the last layer, which is the output layer. Just to recap quickly what we've just done. So we pass in a layer information through our initial constructor, which then just constructs our neuron matrix and our weights matrix in the two methods that we wrote. And now we have a feed-forward method which actually calculates our output values for us given a set of input. Now the next thing that we need to do is actually write a mutation method. I will not be writing a method for sexual reproduction. I will only be writing for asexual, where we're just mutating the weights around, and we're just going to call it mutate, which will iterate through all the values in our weights matrix and just mutate it a little bit based on chance. So we're iterating through all the layers in the weight matrix, then we iterate through all the current neurons, and then we iterate through every single connection that that neuron is connected to in the previous layer. So we get that weight value here, and now we're just going to apply some mutation to it. Then we're just going to place the weight back into the location. I'm just getting a random number between 0 and 1000, and we will apply our mutations based on this number here. A kind of naive way of doing it would be just mutating this weight again based on some chance, but we're going to apply 4 different types of mutations to this weight based on chance. So now I've just written if statements for 4 different types of mutation, and for each given weight there is a 0.8% chance that a mutation will occur, where each mutation has a 0.2% chance. So the first type of mutation will just flip the sign by -1. The second type of mutation will just find another weight between -0.5 and 0.5. The third type of mutation will increase the weight factor randomly by 0 to 100%, and the next type of mutation will just decrease it by 0 to 100%. So this is just kind of 4 different types of mutations that our neural network can have. Now every time we want to mutate a neural network, we'll just call this method, and it should mutate our weights just a tiny bit. So the one last thing that we need to do is write a deep copy constructor, where we basically pass in a copy neural network. This could be anything. This could be the parent neural network, and we need to create a deep copy of it. If you guys don't know what deep copy means, it's basically copying everything that can be referenced, so that making a change in this neural network will not affect the copied neural network. Similarly to what we did up here, you know, we couldn't just go this dot layers is equal to this, because if we ever made change to this layer, the original layer that has been passed into this constructor would be affected. So similarly here, our weights and the neurons has to be deep copied. So now we've just done a deep copy of our layers from the copy network, and we don't even need to do a deep copy of our neurons, because we can just call our initialize neuron method, and it's just going to create our neuron matrix for us. So to deep copy our weights, what we're actually going to do is first generate our weights matrix. So just copy the initial weights method and just call it here. Now we're going to have to write another method called copy weights. So now our copy weights is going to have a parameter called copy weight, where we're just going to pass in the weights from the neural network that has been passed into our constructor. Similarly to how we iterated through all the weights in our mutation method, we're just going to iterate through all the weights, but instead we're just going to copy the weight from this to the newly constructed weight matrix. So just like we iterated through all the weights in our mutation method, we're iterating through them the similar way here, but we're just basically setting the weights, every single weight, to the copy weight. I think we're pretty much now done our neural network file. It's only about 200 lines, which isn't a lot, considering this coding standard that I generally use. Alright guys, I've quickly just written this boomerang. Well, I'm not sure what I'm calling it. I'm calling these like boomerangs, and then they try to get to this spinning hexagon. But this boomerangs are using that neural network file that we just wrote. And they're basically learning to head towards this thing to maximize their fitness. So this just shows that our neural network is working, and it's working properly. So I've made 2 main changes. First of all, I've removed that random variable that we set, and I'm basically just using Unity Engine's built-in random function, which is just unityengine.random.range, and then you can just give it a range between 2 amounts, and it does it automatically for you. I'm not sure why my random variable wasn't working, so I just I'll figure it out later. I just removed it for now. The next thing that I've added is fitness, also eye comparable. I'll go over that in a second. So fitness, it can have a fitness stat added to it, or a set, or we can get the fitness from it. And that eye comparable is basically comparing method. This is used for sorting. We can check whether this current neural network is greater than or less than any other neural network when we want to sort it based on the fitness of the 2 neural networks. And they'll basically get sorted where the smallest neural network will be at the lowest index, and then the neural network where the highest fitness will be at the last index. There are basically two new files, the manager.cs and boomerang.cs. The boomerang.cs basically just gets the position of that hexagon, and it gets the neural network. And basically once it gets these two, it can start updating itself. The input to the boomerang is the angle that it needs to turn to be able to see the hexagon. What is the change in angle that needs to happen for it to be able to be pointing towards the hexagon? So that's the input, and the output is just the angular velocity that it needs to set, which gets set over here. The fitness just ends up being, well, how much has this already turned? Like, how close is it to looking directly at the hexagon? So if it's looking completely away, then it has the lowest fitness, and if it's looking directly at the hexagon, then it starts getting very high fitness. This is where the sorting process happens. I'm keeping the top 50% neural network, and I'm creating mutated copies of them in the other half of the population. Something that I can't emphasize enough, and I think this really is a misconception among the evolution simulator community, is that neural networks are hard. They're not hard. They are the easiest part of a evolution simulator. The hardest part is essentially optimizing and solving other problems that come across as you're doing them. For example, the hardest thing that I can think of in ELSIS is definitely not the neural network, and I've written basically 3 of them. I wrote the initial neural network for it that we've just written right now, a bit more modified version of it. I wrote NEAT for it, and then I wrote recurrent neural network for it, which is currently in ELSIS 2.5. And I've never found these 3 to be hard. I found them annoying, but I've definitely not found it hard writing them. I have definitely found the threading part hard, and I've definitely found writing the rendering backlog list pretty difficult. By watching this video, at least you guys can have a little bit of an idea that if you're trying to make your own evolution simulator, you really should focus more on problems such as optimization than the actual neural network. Please let me know if you thought this tutorial was helpful to you guys, or what I can improve on when I'm making future tutorials. I've been rewatching some of the clips that I've done, and I'm not sure if I'm explaining things properly. I think I'm explaining things at a much faster pace than I should be, but I am under the assumption that you guys have at least some experience in programming. So definitely leave a comment if you think that I should improve somehow. But other than that, I hope this was a helpful tutorial, and I hope you guys can take this project. And by the way, the project link, the actual Unity files, will be in the description, so you guys can play around with the code if you like, or create your own project. And definitely let me know what I can do to improve. Thanks for watching. Bye.